Welcome to this explainer. When we sit down and actually interact with modern AI, it can honestly feel like pure magic, right? It writes poetry, it can help diagnose diseases, and it chats with us like an old friend. But behind that incredible illusion of a thinking, breathing mind, there isn't actually a ghost in the machine. There is just math. Really, really big math. So in this explainer, we're going to take a bottom-up journey to completely demystify artificial intelligence. We're going to strip away all that magic and look at the foundational mathematics that actually power these massive systems. We'll go from a single, simple equation all the way up to the large language models that are literally changing the world today.
Okay, let's dive right into this. Here is our roadmap for today. We'll start by unpacking the illusion of intelligence, then look at the anatomy of an AI brain. From there, we'll cover how training is basically just trial and error, look at the physical chips powering all this math, and wrap up with transformers and language models. All right, section 1, the illusion of intelligence. Math over magic.
So to really understand AI, we actually have to unlearn how we experience the world. See, we look at a picture and we immediately see a shape, but a computer, it only sees math. If you take an image of the number 8 and zoom all the way in, it's just a grid of tiny blocks, right? Pixels. The computer literally just sees a matrix of numbers. Each of those little blocks is assigned a numerical value that denotes its intensity. A number closer to 0 might represent a darker shade, while a higher number represents a lighter one. That's it. The machine learning model is just looking at these vast, incredibly dense tables of numbers, trying to find statistical patterns hidden in the digits. And this mathematical illusion, it isn't an overnight success story. It's an evolution. All the way back in 1943, a neuroscientist named Warren McCullough and a logician named Walter Pitts realized something huge. Human brain neurons actually perform basic logical operations. So they proposed the very first mathematical model of an artificial neuron. But progress kind of stalled out. In 1969, Marvin Minsky published a book called Perceptrons that pointed out the severe mathematical limitations of those early models, which actually triggered an AI winter where funding just completely dried up. It wasn't until the 1980s that a mathematical breakthrough called backpropagation revived the whole field. And finally, in the 2010s, thanks to massive datasets and super powerful new computer chips, we entered the deep learning boom that we're all living through today. Moving on to Section 2, Anatomy of an AI Brain, Building from Scratch. To understand how these models achieve such incredible feats today, we need to strip it back and look at the absolute simplest component. Think about a biological neuron from your brain. Neurons are connected by synapses that transmit electrical signals, and that's what allows for complex thought and memory. Now, compare that to its software equivalent, the artificial neuron. It works in a strikingly similar way. Just like the biological version receives an electrical impulse, the artificial neuron takes in numerical inputs, like those pixel values we just talked about. It applies a mathematical transformation to those numbers and then just passes the result forward. But how on earth does a math equation actually hold information? Well, it does this through two absolutely crucial parameters, weights and biases. Think of these as the internal knobs or dials of the AI. Weights act exactly like the synaptic strength in a biological brain. They represent how strongly one neuron is connected to the next one. Biases, on the other hand, are an extra little mathematical nudge. It's just a number added at the end to shift the result left or right to better fit the data. And here is the crazy part. When an AI learns, all it is really doing is adjusting these specific weights and biases. Now, when you string hundreds or even thousands of these individual neurons together, you get an artificial neural network. The data flows in a single direction. It enters through the input layer. Then it passes through what we call the hidden layers, and this is where the heavy mathematical lifting actually happens. This is where features and patterns are extracted from the numbers. Finally, the data emerges at the output layer as a final prediction. That could be predicting whether an image is a dog or a cat, or even what the very next word in a sentence should be. Which brings us to Section 3, Training, Trial and Error. Basically, learning by making mistakes. So an untrained neural network is basically a brain filled with random static. It doesn't know anything yet. It learns a lot like an athlete learning to throw darts, through continuous feedback and trial and error. But here is the really critical question. If this thing is just processing math, how does the network actually know when it makes a mistake? If it looks at a picture of an elephant but it guesses lion, how does it mathematically understand that it missed the target? Well, it uses a brilliant 3-step procedural loop. Step 1 is forward propagation.
Basically, the AI makes a guess based on its current totally random weights. Step 2 is the cost function, which is often calculated using something called mean squared error, or MSE. The AI compares its guess to the true answer and calculates the exact mathematical distance between the two. That physical distance, that is the error. And then step 3, this is where the real magic happens: backpropagation. Using a principle from calculus called the chain rule, the AI propagates that error backward through the entire network. It tweaks every single weight and bias just a tiny microscopic fraction of an amount so that the next time it makes a guess, the error will be slightly smaller. The absolute crucial takeaway here is that this cycle of predict, measure the error, adjust the weights, repeats millions or even billions of times. That is the big secret to AI. There is no spontaneous consciousness waking up in the machine. It is quite literally just gradient descent and backpropagation, a simple, repetitive loop happening at a scale that is honestly nearly incomprehensible to the human mind.
All right, section 4, the chips powering the math. Because this mathematical loop has to happen billions of times, your standard household laptop is simply not going to cut it. It would take forever. So we have to pivot to the physical reality of AI. You see, the CPU inside a standard computer is brilliant at being a generalist. It executes commands sequentially, one after the other, very, very quickly. But training a neural network requires doing thousands of math equations simultaneously. For that, we need parallel processing. We need GPUs and TPUs. So here is a quick breakdown of the hardware revolution that's actually making AI possible. First up, GPUs, or graphics processing units. These were originally built to render video game graphics by calculating thousands of pixels at once on your screen. But researchers eventually realized they are absolutely perfect for the massive matrix multiplications required for neural networks. Then you have TPUs, tensor processing units. These are specialized accelerators developed by Google, specifically tailored just for machine learning workloads. ASICs are custom-built, hyper-specialized chips locked into doing one specific AI task incredibly well. And finally, NPUs are neural processing units, modern add-ons that allow standard processors to handle complex deep learning tasks efficiently. To truly grasp why we need this specialized hardware, just take a look at this number: 306 stillion. That's a 3 with 23 zeros after it. That is 300 billion trillion floating point calculations. According to OpenAI, that is roughly what it took to train the GPT-3 model. That requires tens of thousands of the world's most advanced chips running constantly for months, consuming massive amounts of electricity just to turn those virtual weight knobs until the model finally gets smart. It's staggering. Section 5, Transformers and Language Models. Let's see how language becomes math. Let's see how all of this builds into the AI you interact with every single day, like ChatGPT. Remember earlier how we said AI doesn't actually understand language, it only understands numbers? Well, researchers figured out a genius way to map words into high-dimensional space as vectors. And when you do that, human language becomes spatial math. For example, if you take the mathematical vector for the word biggest, subtract the vector for big, and then add the vector for small, the resulting mathematical coordinate lands almost exactly on the word smallest. It captures analogies too. The spatial distance between Paris and France is the exact same as the distance between Berlin and Germany. It is literally just vector arithmetic. But the real game changer that led to modern AI was the transformer architecture, and specifically something called the attention mechanism. Imagine the sentence, John wants his bank to cash the check. How does the AI know who his refers to? In a transformer, every word acts kind of like a matchmaking service. The word his sends out a query vector looking for a male noun. The word John has a key vector broadcasting that it is a male noun. They find each other, they match, and the network transfers the context. And this happens simultaneously for every single word in a passage, which allows the model to process context in parallel rather than reading sequentially left to right. Yet, despite this breathtaking complexity, the parallel processing, the billions of parameters, the attention mechanisms, linguists often refer to these models as stochastic parrots. Why? Because at the end of the day, they are deeply complex statistical engines designed to do just one thing: calculate the probability of the very next token or word in a sequence. There is no rational understanding of truth, there's no lived experience, there is no soul in the machine. It is a purely deterministic mathematical process. Which leaves us with this final, really profound question. If an AI is just a giant math equation, a vast collection of interconnected weights and biases multiplying numbers in a silicon chip, why does it feel so undeniably human when we talk to it? Well, perhaps the answer isn't that the machine has become human. Perhaps it's just that these models act as a perfect cultural mirror. They have ingested all of human writing, our fears, our humor, our knowledge, and they are just reflecting it back to us through math. When we gaze into that mirror, we're really just seeing ourselves. Thank you for joining me on this explainer. If you enjoyed taking a look under the hood of tomorrow's technology, be sure to subscribe for more explainers as we continue to unpack the fascinating systems shaping our world. See you next time.